Hi all chemistries, here in this video we are analyzing CSIR June 2011 chemical sciences. Just look at the given problem. In the ruthenium cluster containing 8 coordinated ruthenium centers, the hydrogen atoms are both terminal, one terminal and other bridging, both bridging between 2 ruthenium centers, both bridging between 3 ruthenium centers. First thing, one should count the total electrons on the given ruthenium cluster. We know that hydrogen contributes 1 electron, each ruthenium contribute 8 electrons. Okay, we have 6 ruthenium and each CO contribute 2 electrons. We have 18 CO ligands. So total electron counts equals to 86. And now one should calculate number of metal-metal bonds. We have the formula to find number of metal-metal bonds as total valency electron count equals to 18x minus 2y. Here x indicating the number of metals in the given metal cluster or metal complex, and y indicates number of metal-metal bonds. Now, so whenever we calculate, we can get 11 metal-metal bonds with 86 electrons, which is showing octahedron. Okay, that's why here we can say it as a distorted octahedron. For distorted octahedron, each hydride bridging between 3 ruthenium. Okay, right. And just remember or just note down this important information. Whenever the species or the metal complex containing 48 electrons with 3 metal-metal bonds, it is triangle. And whenever total electron count is 50 with 2 metal-metal bonds, it is linear or bent. Whenever it is 62 electrons with 5 metal-metal bonds, it is butterfly. Okay, and whenever it is 84 electrons with 12 metal-metal bonds, it is bicarbonate tetrahedron, like that. So just note down, this is very important information for you. Next one, in the hydroformylation reaction, the intermediate simply forms acyl intermediate, and this is the correct statements. Okay, so we can observe acyl intermediate in hydroformylation reaction. So first statement is the correct one. Next question here. Statement 1, the size of zirconium and hafnium are similar. Statement 2, the sizes of hafnium is affected by lanthanide contraction. So both statements are correct statements, and the second statement is the correct explanation for the first statement, because hafnium size is affected by lanthanide contraction. That's why zirconium and hafnium have almost similar sizes. Okay, next question, consider the compounds tin tetrafluoride, trialkyl tin chloride. The nuclear quadrupole splittings are observed for. Just remember that s electron density contributes for quadrupole splitting. Okay, now here tin tetrafluoride considered as ionic compound where tin is in +4 acceleration state. That's why s orbital doesn't have electron density, so no quadrupole splitting is observed for tin tetrafluoride. Okay, next question, next species, tin tetrachloride, where tin tetrachloride is considered as covalent compound where tin is in sp3 hybridization. Okay, so s orbital contribution is there in tin tetrachloride. That's why quadrupole splitting is observed in it. Now trialkyl tin chloride, which is also considered as covalent in nature, and where tin is in sp3 hybridization and s electron density contributes quadrupole splitting here also. Okay, next question, chromium 2 and ruthenium +3 and chromium +3 to cobalt +3, the rate of acceleration is going from a outer sphere to inner sphere mechanism is lower for 1 related to 2. Okay, so how and why we need to find. Now just look at the concept here. For chromium +2, which is considered as a high spin in nature, in that case the 4 electrons are occupied in T2G and EG like this, and here T2G is considered as pi2 pi star orbitals and EG considered as sigma star. Okay, right, and now the highest occupied molecular orbital is sigma star in chromium +2, whereas if you observe cobalt +3, where all the 6 electrons are filled in T2G or occupied in T2G only, and here the LUMO is sigma star. Okay, right. Why all the 6 electrons are paired up in cobalt plus 3? That is just due to cobalt plus 3, regardless of the strengths of the ligands. Most of the cobalt plus 3 complexes are strong field in nature, except cobalt complexes with fluorine, which are high spin in nature. Just remember that. Okay, right. And here you can observe that sigma star to sigma star transition. That's why sigma star to sigma star transitions are involving faster inner sphere mechanism. Okay, right. And next one, chromium plus 2 to ruthenium plus 3, where you can observe highest occupied molecular orbital is sigma star, and the lowest occupied molecular orbital on ruthenium plus 3 is LUMO, that is on pi to pi star orbital. So the transfer from sigma star to 5 star, so this transition is lowest speed. Okay, that is 10 power 2, acceleration is 10 power 2 for this. That's why this transition is slowest one. Okay, the first transition is slowest one just due to the transition from sigma star to 5 star. Okay, sigma star HOMO to 5 star LUMO. Okay, next question, the correct value of isomer shift in mass bar and its explanation for iron plus 2 TPP and iron plus 3 TPP respectively from the following. Here TPP indicating tetraphenyl parpyrenate. Okay, 0.52 mm per second, 0.45 mm per second, increasing in s electron density, decreasing in s electron density. Right, here both iron plus 2 and iron plus 3 complexes are square planar in nature, because here TPP is a tetradentate parpyrenic type ligand, and which making iron plus 2 and iron plus 3 is in square planar complexes or square planar geometry. Okay, right. And both iron plus 2 and iron plus 3 involving DsP2. Okay, DsP2 hybridization. That's why s electron density responsible for quadrupole movement. And here iron plus 2 is having higher s electron density when we compared with iron plus 3. That's why higher isomeric shift for iron plus 2 complex when we compared with iron plus 3 complex. Okay, right. In IR spectrum of cobalt complex, the COH stretch is observed at 1840. The COD stretch in the given cobalt complex is. Here we need to use the formula or equation of as frequency of vibration equals to 1 by 2 pi under root k by mu. Here k is force constant, mu is reduced mass. Okay, ratio of frequency or wave number nu bar of COD and COH. So by just taking that, by just substitute the reduced masses, and we can get 1 by under root 2, and from that we can calculate the nu bar of COD as 1840 by under root 2 1300. Okay, for the complexes, the just observe the complexes nickel, manganese, and the next one is chromium and titanium. The ideal octahedral geometry will not be observed in. Okay, and just to look at the first nickel plus 2 complex where 8 electrons are there, you can see T2G and EG are symmetrically filled, and for Mn plus 2 where 5 electrons are symmetrically filled because water is a weak field ligand, and in chromium complex also 3 electrons are filled in T2G in symmetrical way, and whereas in titanium plus 3 only 1 electron is there in T2G. That's why we can consider it is unsymmetrically filled, and unsymmetrically filled orbitals leads to deviations, that is John Teller distortions are observed in titanium plus 3 complex here. That's why ideal octahedral geometry is not observed for the 4th complex. Okay, and next question, among the following the number of anhydrates of acids, or so here whenever B2O3 reacts with taken in water produces boric acid, N2O5 produces HNO3, SO3 produces H2SO4, and P4O10 produces H3PO4. That's why these are all anhydrates of acids. Whereas if you look at the reactions of CO in water produces carbon dioxide, NO in water produces different compositions, produces ammonia and NO2, and in the presence of more acidic conditions they can produce acids. Okay, that's why here CO and NO are eliminated because they are not hydrides of acids here. Okay, next question. For a given nuclear fission reactions of uranium-235, just observe, okay, the amount of energy in kilojoule per mole released during this process is here given. Mass of uranium-235, barium and krypton and neutrons are given. Okay, and here just observe the fission reaction. Energy released per atom is equals to delta M into C square. So here delta M is that means mass of uranium plus mass of neutron minus mass of barium plus mass of krypton plus 3 moles of mass of neutron into C square. Okay, just substitute all the mass values which are given in the information of the problem, and C equals to 3 into 10 power 8. Okay, just substitute it and we can get E value, that is energy released per atom equals to 2.8 into 10 power minus 11 joules. Now energy released from 1 mole of disintegration of uranium-235 equals to energy per atom into Avogadro number. So Avogadro number is 6.023 10 power 23, and from that we can get 1.68 into 10 power 10 kilojoules. Okay, right. Thank you very much.